Hey guys, welcome to our first video about the Pythagorean theorem in rational numbers. Today we're going to talk about different types of numbers, classify different sets of numbers, and look at a few examples. We'll look at the whole number and rational number song that some of you have seen in the past. So we'll look at that as an example of a few things that we're going to do. First thing I want to show you is, actually on your papers, I want you to answer this question here. So the question says, I'm thinking of a number between 1 and 10. Whoops. Thinking of a number between 1 and 10. What if I give you 3 guesses? Could you figure out what that number is? What if I give you 8 guesses? So I'm thinking of this number. If I give you 8 guesses between 1 and 10, you think you can figure it out? I want you to write down how many guesses you would need in order to be certain of what that number is. So just write that down for me. And we'll kind of talk about that. I don't want you to change your answer after we figure this out, but I just want your initial reactions. We'll do a little secret video code every time just so I can see that you're actually watching through the videos. This one, what I'd like you to do is write down any number that's a multiple of 6. So in that box, put any number that's a multiple of 6. And that way I'll be able to see if you're watching the videos and getting the codes there. That way, if your friends are looking at your thing there, they can say, you can just say, oh, I wrote down a number. You just write down a number, and they might get it wrong. So let's go back and take a look at a few things here. Here's the number system, and numbers are all classified. The biggest category that we'll know is real numbers, and that's broken down into rational numbers and numbers that are irrational, and that's our learning target for today. Kind of define what real number or what rational numbers are and what irrational numbers are. There's actually some other types of numbers that aren't even real numbers, kind of outside of this whole thing that you'll talk about later on in high school. So the real number system kind of breaks down into and gets smaller and smaller. Rational numbers, and then the starting point are the what are called natural numbers, and those numbers are the counting numbers. Let me get that a little smaller. Counting numbers like 0, 1, 2, 3, 4. I almost said 0. But we start with 1, 2, 3, and so on. The numbers that you count, if you're picking up objects and counting them. After that, we do want to include whole numbers, and that just includes 0. 0 is also included as is classified as a whole number. So we have whole numbers are 0 and all the other counting numbers, positives. After that, we have integers. And integers just add in the negative whole numbers. So -3, -2, and so on. 14, 100, those are all integers. Okay. Rational numbers are numbers that can be written as fractions. So now we've included all the other numbers other than just the whole numbers. This is where you'll see things like 1/2. Okay. And you also know other numbers like 3.2. We'll talk about why that's rational today. And then anything that's irrational is numbers that we can't write as a fraction. So anything, and these are a little harder to come up with because there aren't as many. Actually, this circle should be a little bit smaller in comparison to the rational numbers. I'll show you another organization system for it all as well in a second. But anything that's irrational is anything that can't be written as a fraction. So some examples of that, like a lot of people know, are pi. And then if you type in a couple like square roots on your calculator, if you do square root of 2, if you actually type in that decimal and see what you get, it'll be a number that the decimal keeps going on forever, and you don't see an ending to it. Your calculator obviously ends, but it gives you 1.414213562. It actually keeps going on after that. And you notice there's some numbers that show up twice, but there's no repeating pattern in there. So this is the number system, and I just wanted to show you, and some of you have seen this, but I want to show you the another organization system of it. Notice the natural numbers are the smallest numbers, and they just keep adding on numbers as you're working out new types of numbers. Things you'll look at high school are imaginary numbers. Those are kind of outside of the real numbers. Notice that irrational numbers are pretty relatively small in comparison. Alright, so if you could push pause, and I'll have you write this number system down for me. So you can write either this one down if you want to, or this organization system. So push pause and write that down. Okay, Next example here we'll look at is just a quick introduction to that rational number song in the video here. So I'll put that up. Here it is.
Natural numbers are naturally numbers you count on your hands and your feet. 1, 2, 3, 4, 5, 6, and so on. Whole numbers are natural numbers plus 0. That's the only difference. Oh, 0, 1, 2, 3, and so on. Integers are whole numbers plus negatives. They look a little bit like this. -2, -1, 0, 1, and so on. Last but not least, not to be undone, rational numbers are integers and fractions like -3, 1/2, 5/8, and 14.2. All natural numbers are whole numbers. All whole numbers are integers. All integers are rational numbers. Now listen to that drummer. All natural numbers are whole numbers. All whole numbers are integers. All integers are rational numbers.
One dots. So if you have the picture drawn here, a rational number is a number that can be written as a fraction. Or a ratio of two integers. So a fraction of a over b, where a and b are integers. So any number that you can write as a fraction is a rational number. An irrational number is kind of pretty much the opposite of that, a number that can't be written as a fraction. Okay, so a few examples of that. A number that can be written as a fraction can be. A rational number would be things like, obvious fractions already, 2/3 or 3/2 or, 1/2 or, 1/13, things like that. But also just whole numbers like 6, because we could just make that 6/1. And I'll ask you to prove that by just making it a number that goes over 1. So irrational numbers are things like pi, and square roots of non-perfect squares, like square root of 2 or square root of 17. We couldn't use square root of 16 because that would be just 4, which is rational. So that last one there wouldn't be a good example. Okay, so now we have a few more just types of numbers that we're going to look at here. Terminating decimals, things like 0.3257884, okay, or 0.2, or 0.752. All of these decimals have something in common in that they end. Terminating decimals, ones that end, are rational. And this has to do with place value. You can make 0.2 into 2/10ths because it's in the 10th position. Or 752, that's 752 thousandths. And again, it's tenths, hundredths, thousandths place. So it's 752 over 1,000. Next one, repeating decimals are also rational. Probably the most common repeating decimal that people see is 0.3333. Keep going on. That's really just 0.3 with that bar over it. And I imagine you remember that that's just 1/3. Okay. And we'll show you why that works. But anything that repeats, even like 0.123, and the 3 keeps going on, if you see a bar over that, there's a way to write that as a fraction. And I'll show you how to do that in a little while. There's also things like 0.22. Different parts of things can be repeating, and all those are actually rational numbers as well. A decimal that doesn't terminate or doesn't end and doesn't repeat is what's called an irrational number. Okay, and those types of things are pi, like 3.1415, whatever it is. Keep going there. Your calculator shows that it ends, but it actually just keeps going on forever and ever and ever. And then a few other examples of that are things like square roots of non-perfect squares. So those things, that pattern just never shows up. Okay, sorry, I should have made that bigger. Okay, so we'll talk about irrational and rational and say why. So first one, we're looking at a fraction. If it's a fraction already, it's rational. So we can say that this one is rational, and it's a fraction already. We know that the next one's square root of 100. If you think about doing the square root of 100, you could use your calculator for that. That's just 10. So we have 10, that's a whole number. But 10 can also be 10 over 1. Those are the same things. So it's rational. And again, I'm just kind of abbreviating a few things. The square root of 6, if we type that in to our calculator, we actually don't get, we can see what that is, but the square root of 6 isn't a perfect square. If you type that in, you get 2.44948. And it keeps going. And notice we had some decimals that were like repeated. You see the 4 multiple times, but there's no pattern. Like you don't know what's coming next. So since that one is non-terminating, and you don't really know that from your calculator screen because your calculator ends, but it's going to keep going on forever. And it's also non-repeating, so it's irrational. Okay. Square root of 16 over 25. If we do the square root of 16 and 25, that's 4 over 5, so that's rational. Negative 2/9, that's a fraction already. Negative numbers are also rational numbers. And also mixed numbers, 4 and 13/25, that's also a rational number. You can do that little trick where you do 25 times 4, which is 100, plus 13, so it's 113 over 25. So that's a rational number. Now the next thing we'll do is write 0.45 as a fraction. Once again, tenths, hundredths, thousandths, places, thinking about those. This is actually 45 over, and this is the tenths, hundredths place, so it's 45 over 100, and we'll simplify that. We'll divide each by 5. And get 9 over 20, I believe, and that's the simplest form of that number. The next thing we're going to talk about is writing decimals that actually repeat as a fraction in simplest form. Now a lot of people will think, oh, it's just 0.5, so that's 5 over 10 because it's in the 10th position. So 5/10 is 1/2, and we got it. But really, if you think about that, that 0.5 keeps going on forever. So if we stop at certain places, we could write that as 55 over 100. But if we add another 5, that would be 55 or 555 over 1,000. Okay, so we just keep going on. This process doesn't end. So there's a little trick that you can do. If it repeats if one digit is repeated, you just take that number and put it over 9 actually. So that's 5/9. And I'll talk a little bit more in class about why that works. Right now I'll go ahead and show you just real quick how that works. 0.5 repeating, if you think about that, that 0.5 is going to keep going on forever. So 0.5 repeating, that 5s are really going on forever there. If you multiply that by a 10, if you take that 0.5 and multiply it by 10 and move that decimal over once, so that would become 5.5 repeating. So the 5s are just going to keep going on. And what we can do is actually subtract these guys. What happens is all these 5s are going to cancel out because they're after that decimal. And we have to subtract 5 from 0 now. 5 minus 0 is just 5. But what I did was I took this original one, we'll call it x. This top one, we multiplied it by 10. It was 10 times bigger. So if we're subtracting this equation, 10 minus 1 is 9. So the equation works out that if you divide by 9, you get x equals 5/9. And that's kind of why that works. Okay. Next part here we'll look at approximating roots, and we'll do a lot more of this tomorrow. But if you think about the square roots of perfect squares, you list them all out. We have 64, and I'm just starting closer to 152 here. 64, 81, 100, 121, 144, and 13 squared is 169, and you can kind of list all those out. But this is 12 squared and 13 squared. So we know that 152 would be somewhere in between those guys. So if 12 squared is 144, and 13 squared is 169, we know that 152 is somewhere in between these guys. And it's actually, if you do subtraction, figure out which one it's closer to. 144 is a distance of 8 there. And this guy's a distance of much more than that. Be 17, I think, if I did that math right. So it's actually going to be closer to 13 squared. So it falls between 12 and 13. Alright, and the last thing we'll look at here. I'll let you kind of figure this out. We'll go over this one tomorrow here. We'll go ahead and stop the video here, but thanks for listening there, and we'll see you guys tomorrow.